remember what the energy is, right? So first of all, we have n indistinguishable particles, so let's already put 1 over n half here. And then we have imagine that we have e to the beta h, and for each particle we'll have the same kinetic energy and the same potential energy. Everything will be the same, right? So we'll have we'll have e to the beta times, and we'll have the energy of particle 1, kinetic energy of particle 1, plus potential energy of particle 1, kinetic energy of particle 2, and like that. So we just have all these energies here, right? And because those energies are decoupled, the particles don't interact, we can write this as a product, right? I could just write it like this, times e to the beta times that, right? It's all the same. So it's going to look like the same thing raised to the power n. So we can already write that here now. So we just have to write down the partition function for a single particle and raise it to the power n. And this is also a standard scenario. This is usually what happens. If you have lots of identical particles, all you have to do is calculate the partition function for one particle and just raise it to the power n, because it's the same for all the other ones. Okay, so now let's actually write down the thing in detail. So we have e to the minus 1 over kt. And then we have to write all these terms out. So let's write it out even though it's tedious. We have px squared over 2m plus py squared over 2m plus pz squared over 2m plus p theta squared over 2I plus p phi squared over 2I sine squared theta. So that's the kinetic energy. And then we have the potential energy, which is going to be minus mu permanent E dot L minus 1/2 alpha E dot L squared. And that's it, right? Oh, plus the box, right? Plus U box. All right, that's it. And then we have to raise this whole business to the power n. Okay, so now we have to write in here all the dp's and dq's. So we have dpx, and then the corresponding coordinate is just x, right? So I write dx, and then we divide this by h. And then dpy, dy divided by h. And then we have dpz, dz divided by h. And then we have dp theta, what is the coordinate that goes with, it's just theta, so we have d theta over h. And we have dp phi, d phi over h. That's it. And now we have to integrate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. We can do it. All right. So, what are the limits of px? It goes from where to where?
From minus infinity.
Right. So minus infinity to plus infinity. So we are now just looking at this term, right? That's the only place px appears. So what do? So we really just have e to the something px squared times dpx. So that's like e to the minus x squared dx from minus infinity to infinity. So we want to change variables, right? We want to change variables so we can call this whole thing as something squared. And so to do that, I have to multiply and divide by the same thing, which is the square root of kt2m. Okay, is everybody together on this? So I multiply and divide by that. So I first multiply by that, which is going to be kt2m. I multiply and then I divide. Then I have a new variable here, and that new variable, we call it anything. Then we integrate, we get root pi, right? So we just put a pi in here somewhere. Put a pi in here somewhere. So now we have done the integral over px. We still have an h now. Now I'll do the same thing for py. The same. pz, the same. So we'll do it for these three variables, and then I will have this to the 3 halves and h cubed. All right, let's do this guy next here. What happens? We do the same thing. Yeah, so what are the limits of p theta?
Minus pi to pi. 0 to
P theta, P theta. P theta is the angular momentum associated with rotation.
From minus infinity to plus.
Sure, it can go infinitely fast. It can have infinite momentum, just like linear momentum. So this also goes from minus infinity to infinity, so does that. And we use the same trick. We change variables so that this guy ends up being just something squared. So we have to multiply through by the square root of kt times 2I. So I get here the square root of kt times 2I, and I have to multiply again by pi. Okay, and divide by h. And now we're down to this guy, and we do exactly the same thing as before. Right, so now I have to multiply through by kt, the square root of kt 2I sine squared theta. So kt 2I sine squared theta times pi over h.
Can you explain again why is the range of theta and pi is from minus infinity to infinity?
Explain why the root pi?
Why is the range of theta and pi from
It's not theta and pi, it's
P
p
theta.
theta. P theta is angular momentum. Okay, everybody happy with this? Yes.
But each the last term should be in the integral still because it has a theta.
Yeah.
You have an integral with a theta.
We haven't integrated over theta. We haven't done that. We're only integrating over the p.
Yeah, you can put all the rest terms out of the integral symbol because they have no variables.
Right,
But you have the theta, so
That's
this
right.
term should be in the integral.
that's right.
Yeah.
I haven't, yeah, I'm sorry, yeah. There's still the integral here
Okay.
over x, y, z, theta, and phi. Yeah, it still remains there. So, what I wanted to illustrate here, though, is that even though we can integrate out the momenta, we ended up getting something involving the coordinates. Okay, so that's kind of interesting how that comes about. All right, and we still have the potential energy left. Right? So, and so we have e to the potential energy, and then we have dx, dy, dz, d theta, d phi. Okay, now, let me integrate over dx, dy, and dz. And as before, if I'm inside the box, I get 1, because this is 0. Outside the box, I get 0. So the integral of dx, dy, dz, it only appeared here, is just going to be the volume of the box. So we have, in addition to this, the volume of the box. And then we still have remaining e to the, now note that we have a minus sign here, minus signs here, so we have e to the plus 1 over kt times mu p e dot L plus 1 over 2 kt, because we have a 1/2 there, alpha times e dot L squared, and we still have d theta and d phi to integrate over. Now, theta goes from what to what? From 0 to pi, so that's theta. And phi goes from 0 to 2 pi. Good. Okay, so you see that we're almost there. Now, can we do these integrals?
Well, at least over this letter, how do we call it? Side to side. The last one.
Phi.
Fine. So we can integrate over that.
Okay, well, we have to think about this. We have a dot product here between E and L.
But we say that
And
E
we have
is
one
along z-axis and we have no problems.
Right. So the point is that up to now, everything is completely general, right? We haven't specified a coordinate system, right? Things are arbitrary.
And then we can probably even integrate over theta.
So let us choose now a coordinate system so that the electric field is along the z-axis. This is completely general. Now, if E is along z, and so they're not, generally I like to do things in a way where we don't have to worry about where our coordinate system is. That's called covariant formulation, and it's really nice because generally the results are simpler than if you actually choose a specific coordinate system to work with. The advantage is that at the end, you can choose a coordinate system which is convenient. And that's what we are doing here. It's convenient to choose a coordinate system where E is along Z. We could choose any coordinate system, but if you chose one where the electric fields are 45 degrees to the x and y axis, things will be more complicated. So we just choose one where things are simple, which is this one here. If we make, so is everybody happy with that? This is true in any coordinate systems. We can choose a coordinate system so that the z-axis is lined up along E. If we do that, then this will just be the usual cos theta. And this will be cos theta squared. So let's write down z 1 over n factorial, and let's pull out everything that we don't need. So we get these guys coming up. So we have 2 pi mkt to the 3/2, same as for an ideal gas. We have a new contribution where we have 2 pi IKT to the power of 1, because we have this and this. We have an h to the 5th down here. We have a volume here which comes out. And then we still have this term, so we have to integrate over theta and phi, where we have a cos theta here and a cos squared theta here. And as Mikhail said, if we make this choice, phi doesn't appear anywhere up in the exponent. In fact, it doesn't appear anywhere. So we can integrate over phi right away and just get 2 pi coming out. So we have an additional 2 pi, I'll put it here, and then we just have one integral over theta, and we have e to the plus mu p over kt times e times cos theta plus alpha E squared kt times squared theta, and we have a sine theta coming out here. So we have sine theta d theta all to the power n. So that's a partition function. So it's interesting to note that this sine theta d theta, or here we have sine theta d theta d phi, which is the element of solid angle, comes out because we have this sine squared theta in the momentum term, and when we do the integrals, we end up with the sine theta coming out. And if we had chosen a different set of variables, we would still end up with this result. Okay, and now comes the painful part, which is the following. Well, sine theta d theta is just d cos theta. So we could call this x, and this will be minus dx, and we could integrate that. But here we have an e to the plus x squared dx. We cannot integrate that. The whole problem with liquid crystals is that we cannot do this integral to closed form. E to the minus x squared we can integrate from minus infinity. It's the error function, we can do it. But this one, there's no simple closed form solution to that.
And if we add something and subtract something in this exponent to get the total square.
But I don't worry about that. I mean,
Are you
even
sure?
if
Are you
this term
sure?
isn't here, just forget this term.
Yeah.
UP is 0, no permanent dipole. We still cannot integrate e to the cos squared theta, e to the ax squared dx.
Well, from
We cannot
0 to
integrate.
1. But
We cannot integrate. E to the
why currently?
x squared dx. We just cannot integrate.
Oh.
0 to anything. Cannot do it. Numerically, of course, we can do it. There are some functions called Dawson's integral, complex error function. You can do, but you cannot do it simply. Okay, so it's not. The integral is simple. It doesn't. It's well behaved. It doesn't do anything unkind. But it's just a kind of a. It would be nice to be able to do this in closed form. So, but that's fine. Okay, so that's it. So basically we are done. We can write down the free energy, and then we can extract from the free energy anything that we want. So proceeding just like before, the free energy is minus kt log z. So we have to do the usual tricks. We take the logarithm of this guy, use Stirling's formula here, and then we get minus nkt log all this stuff, all of those things, 2 pi mkt to the 3/2, 2 pi I kt to the power of 1, h to the 5th power. We have the volume, and we have an E here, right, because of Stirling's approximation here. And then we're still stuck with this integral here. So we have the 2 pi, we have it here. And then we have this multiplicative integral here. We can write that separately as minus nkt ln just of this integral 0 to pi e to the up E cos theta over kt plus 1/2 alpha E squared over kt cos squared theta d theta sine theta d theta. And
I
we can get,
think the equation in the log is divided by n.
we have already done that. Right? We have,
Because
we have, this n up here,
yeah,
so that gives us this nkt here. And then we have this guy, as we say, and minus kt log n factorial is minus
k
nkt
L log n
Log
divided
n.
e.
e. It's log n minus n when you factor, so it's factor the n, then it's minus 1, and that 1 is an e.
Yeah, n over e. N divided.
Oh, it's n over e, I'm
Yeah.
sorry. Log of n factorial is n log n minus n. It's n times log n minus 1, which is over e. I'm sorry.
Yeah. So because of that,
E in the denominator.
no,
Oh,
there is a e over e divided by n. Product the e over n.
oh, right, there's an, yeah, there's an n down here. Right, that's how it is. I'm sorry. Right. Good. Okay. And so once we have this, we can get everything from the free energy. So let's have a look at the average energy. So the average energy, how do we get the average energy? We do something fun, right? We multiply the free energy by beta first, and then take the partial with respect to beta. So let's do that quickly. Let me replace all the kts by beta, 1 over beta. So here we have, I just take these kts out, so I will have 5 halves up on top, so it'll be beta to the 5 halves down here. And here we'll have a beta. Here we'll have a beta. Okay, so we multiply through by beta. So we take beta times the free energy, and then we take the partial of this with respect to beta. So when we multiply through by beta, this guy is gone and this guy is gone. That's really the purpose of doing that. Then we have to take the derivative of this with respect to beta. So again, beta only appears here, and we can take the minus sign and bring it in, so beta comes up here. And so we'll just have n log beta to the 5 halves. 5 halves comes out, and we just have 5 halves n log beta. The derivative of that is just 1 over beta. So we get 5 halves n times 5 halves 1 over beta. That was pretty easy, like this part here. Here, the beta's gone. And so, but it appears here. So we have a logarithm. So first we take the derivative of the logarithm with respect to its argument, which gives us 1 over the argument, and then the derivative of the argument with respect to beta. And when we do that, we have an e to the beta times this. So basically we end up with taking the derivative of the exponential with respect to the exponent, which just leaves the exponential unchanged, and then the derivative of the exponent with respect to beta, which is just this guy here. So when everything is said and done, we get minus n over beta, so I'm continuing that line, n over beta times 1 over this integral e to the mu p over kt e cos theta plus alpha e squared over 2kt cos squared theta sine theta d theta. So that's where we put the derivative with respect to the argument. And then up here we have the integral, which is going to be just mu p e cos theta plus alpha e squared over 2kt cos squared theta times e to the mu p over kt e cos theta plus alpha e squared over 2kt cos squared theta times d times sine theta d theta. So that's kind of interesting. So this part certainly makes sense, just the way it did for the ideal gas. We have half kT of energy associated with each degree of freedom.
Ask a question.
Yeah?
The n divided by beta, where's that from?
Yeah.
You multiply the f by beta, does that cancel? Didn't that cancel?
Oh, I'm sorry, you're right. This is gone.
And
That's gone.
the 2kt, I thought you, on the top, on the numerator, on the left, I thought you taking beta out from there.
I have. Very good. Good. Okay, average energy. So we have 5 halves nkt minus n times, and I want you to meditate a little on this expression here. This term here has a cosine theta, and then it has a Boltzmann factor, and an integral over the angle. So this Boltzmann factor, this guy here, divided by this, is just the probability that our particle has orientation cos theta. So we can think of this term here is just cosine theta times the probability of having orientation theta integrated over all theta. So we just end up getting the, I'll write it like this, plus minus mu p e cos theta average plus n times from the second term minus 1/2 alpha e squared cos squared theta average. And so intuitively this has a nice interpretation. This is just the usual kinetic energy associated with translation plus 2 more degrees of freedom associated with rotation, half kT of energy associated with each of those modes. And then we have the average energy. The average energy of a molecule with the electric field due to its permanent dipole moment, and the average energy associated with the induced dipole moment. So that's kind of what we would expect. And I guess one important thing is that we find that what we have here is n times minus mu pe, which is a constant, times cos theta. And this guy is minus n times 1/2 alpha e squared, the average and cos squared theta. So in these average energy expressions, we find that the relevant quantities are the average value of cosine theta and the average value of cos squared theta. And so these are quantities that are really order parameters because they tell you something about the average orientation of the rods inside. And if you want to do this in a coordinate independent way, you could also think of this as L dot E hat, which is whatever direction you have the electric field. You take the average of this, and this guy is L dot E hat squared average. So one interesting thing that comes out of this picture is that we find that in order to describe the average energy, for example, we need to know what the average orientation is, measured this way. And this is dipolar order. It depends on which way the arrow on L hat is pointing. And if you have a rod that has no dipolar character, the same n for n, then the relevant order parameter is the average value of cos squared theta, or this guy, which is invariant under changing the sign of L. And so these are things that will be featuring prominently in liquid crystal stuff. So, any questions on this? I'm late. Okay, we'll take it from here. We made an approximation here, which is worth remembering, is that we didn't take into account that if a particle gets really close to the side of the box, it cannot rotate freely. So there's some coupling between position and orientation, but we ignored that. And of course, if you have a big enough box, it doesn't matter. But in general, that's something that you may want to worry about. So, okay, we'll quit here, and then we'll continue.